Okay, in this lecture we take a look at the two-dimensional perfectly inelastic collision. As we'll see, once again, there's lots of similarities between the perfectly inelastic collision and the explosion. So go back to the two-dimensional explosion problem for just a moment. You'll see lots of similarities between that problem and the one that we're about to perform. Okay, so let me go ahead and read the problem to you. Let's copy it down as we go. There's a couple of things that we're going to calculate out here. Okay, two objects of equal mass of 1 kilogram, just to keep the numbers easy to work with. They undergo a perfectly inelastic collision in 2 dimensions. Now the first object is initially moving in the positive x direction with a speed of 1 meter per second. So let me immediately begin to draw that out. Okay, so here's the first object of mass m. This is equal to a kilogram. And it's initially moving like so. Actually, let me draw it like this. Like so, along the positive x-axis with a speed, v1 naught, of 1 meter per second. Okay, the second object, it has the same mass. It's initially moving at the same speed, but the angle that its initial velocity vector makes with respect to the positive x-axis is given as 135 degrees. So how do you even picture that? Well, you have to think of it like this. Like so. So here's the second object, also of mass m equal to a kilogram. Here's its initial velocity vector. The magnitude v2 naught is also 1 meter per second. But with respect to the positive x-axis, off in this direction like so, this angle here, call it theta, is given to us as 135 degrees. And then right here, ultimately, this right here is where the collision takes place, hence my diagram. And then we're going to calculate a couple of things. In part A, we're going to find the final velocity of the two objects after they've collided together, and they've stuck together, remember. It's a perfectly inelastic collision. And then we're also going to calculate the heat loss. Okay, now let's use a little bit of mathematical intuition here with this example. If the two objects have the same mass and the same speed initially, this guy's moving along the positive x-axis and this guy's moving along a 135-degree angle, then probably what's going to happen is this. The two objects will collide and stick together and then probably move off into the first quadrant together. Now they may move off instead into the second quadrant together like so. We don't exactly know what the solution is going to look like. However, all I'm going to simply do is assume that a solution looks a certain way and then set up my equations and go from there. So in other words, I'm just going to intuitively guess the following. I'm going to intuitively guess that the two objects collide together and they end up doing something like this. So here's m and m. And they move off like so with a common final velocity v final. We don't know the magnitude of that vector, nor do we know its direction. So right here is the positive x-axis. So let's go ahead and define an angle associated with this v final. This angle here I'll just refer to as phi. Okay? Okay, and now we set up our expression. So change in momentum of number 1 plus change in momentum of number 2 is equal to 0. Okay, notice that there is no third term here like there was in the two-dimensional explosion problem. So one big difference between the two examples is that in this problem we only have two objects. Keep that in mind. However, like we did in the two-dimensional explosion problem, what we do is we break this up into the x component first and then we break it up into the y component. With a little bit of practice, you could actually just do all of this in one shot, but it takes a little bit of experience to be able to do that easily. So let's go ahead and break it up into the x direction first and then the y direction. Okay, so first of all on the x direction, here's the notation that we'll see. Change of momentum of number 1 in the x direction plus change of momentum of number 2 in the x direction is equal to 0. And now we just start filling in our terms, final minus initial. Okay, so first of all, for the first object, its final momentum in the x direction will be the mass m and then multiplied by the x component of v final. That's going to be v final cosine of the unknown angle phi. Like so. Okay, then minus the initial momentum here of number 1 in the x direction, which is just m times v1 naught, because we remember that we're given that this object is initially moving along the positive x-axis prior to the collision. Okay, now we have object number 2. So its final momentum in the x direction will be its mass m, and then multiplied by the same x component of v final. So m v final cosine phi. And now be careful down here, the initial momentum of the second object in the x direction will be the mass m, and then multiplied by the x component of v2 naught. That's v2 naught cosine theta. theta, like so, and then equals 0 here on the right-hand side. Okay, now here's what we solve for. It occurs twice in the expression. We solve for v final cosine phi, because when we do, we're solving for the x component of the v final vector. In a few moments, once we complete what happens in the x direction, then we just set this up in the y direction, and really the only thing that changes is that all the cosines behind me just alternate signs. At any rate, however, let's go ahead and find v final cosine phi. So to do so, let's go ahead and cancel out the mass m at this point. Remember, it's common to all terms, and now algebraically we'll do this. We'll take this term here and this term here and move them both to the other side. Like so. But then we have this term here and this term here being added together. Like so. And then to get v final cosine by itself, just divide the 2 to the other side. Like so. And now let's go ahead and fill in everything. When I do, if the green v final vector on the top board is in fact in the first quadrant, like I'm guessing, then this should be a positive number. So let's see what happens. So first of all, I have 1 plus 1 times cosine 135. And then all divided by 2. And I do, in fact, get a positive number here. It's about 0.15 or so meters per second. So the x component here, let me write it on the top board for reference. V final cosine phi is this number of about 0.15 meters per second. And now we set this up now in the y direction. So let me go ahead and do some erasing here for the x direction. Okay, and now for the y direction, first of all, the notation. So change of momentum of number 1 in the y direction plus change of momentum of number 2 is equal to 0. Once again, just start filling in the terms. So now, first of all, for object number 1, we need its final momentum in the y direction after the collision. That will be the mass m, and then multiply by the y component of v final, which is v final sine phi. Like so. And then minus the initial momentum of number 1, but in the y direction, that's equal to 0, because this object initially was moving along the positive x-axis. Okay, then object number 2, its final momentum in the y direction after the collision will be its mass m, and then multiplied by the same y component of v final. So that's v final sine phi. And then be careful down here at the bottom of the diagram for the initial velocity, or the initial momentum rather, of number 2 in the y direction. We'll take the mass m and then multiply by the y component of v2 naught. That's v2 naught sine theta. Like so, and then all equals at 0 on the right hand side. And now what we're solving for here in this expression is v final sine phi. Once again, notice that it occurs twice here in the expression. That's the y component of the v final vector. So let's finish the algebra. Let's take this term here and move it to the other side. Before I do, by the way, let's go ahead and cancel out the mass again. All right, so let's take this term here and move it to the other side. Like so. And then add together these two terms here. Like so. Last step is to take the 2 and divide it to the denominator on the other side, like so. And now I've got my v final sine phi. If this is a positive number, then therefore the green v final vector on the top board does in fact point into the first quadrant. Okay, so numerator of the expression is 1 times the sine of 135, and then all just divided by 2. And sure enough, it's a positive number. It's about 0.35 or so meters per second. So then therefore I was correct with my intuitive guess that the v final vector is in fact in the first quadrant. So then therefore the answer to part A of the problem is as follows. In vector form, v final is equal to, first of all, 0.15 I hat, and then plus 0.35 j hat meters per second. We have here a first quadrant vector for v final, like so. Okay, so that's the first portion of the problem. And the second portion of the problem will calculate the heat loss. Once again, it's a non-conservative force of friction that's causing everything to stick together. Therefore, there's going to be heat loss. Now, we calculate the heat loss in part B of this example exactly like we did in the earlier one-dimensional example involving the carts. So here in part B, we now calculate the change in the energy of the system, which is the change in the kinetic energy of number 1 plus the change in the kinetic energy of number 2. Now, of course, recall that kinetic energy is in terms of speeds, not velocities. So then therefore, let's immediately do a little bit of Pythagorean theorem here to find the magnitude of this v final vector. So I'm going to do this off to the side. All right, so the magnitude of the v final vector, if I do the math here, that speed ends up being about 0.38 meters per second. So once again, that was just a little bit of Pythagorean theorem with these components here, and now we'll go ahead and use that speed when we make this calculation. Okay, so first of all, the change in kinetic energy of number 1. Final kinetic energy is 1/2 m v final squared minus the initial 1/2 m v1 naught squared. Then for object number 2, final kinetic energy 1/2 m v final squared. Remember, they're stuck together, same speed. And then minus the initial 1/2 m v2 naught squared. Like so. Now be careful, nothing cancels out here. This is not equal to 0 on this side of the expression. This is some small negative number that we're trying to find. So the 1/2s are there, all of the m's are there, etc. Nothing cancels. This is why we do need the mass of the objects, by the way, in this problem. Remember that they were given as 1 kilogram. All right, so let's go ahead and just punch it all out. So 1/2 times 1 times 0.38 squared minus 1/2 times 1 times 1 squared plus 1/2 times 1 times 0.38 squared, and then minus 1/2 times 1 times 1 squared. So after all of that, once again, we end up with a relatively small amount of energy that's lost as heat. Here in the example, negative 0.86 joules. Once again, it's negative because the final energy of the system is a little bit less than the initial energy because of the heat loss. Okay, so that concludes the two-dimensional, perfectly inelastic collision.